Okay, so this will be for section 1.4, and we're going to revisit continuity today, talking about writing that is good enough for AP, and then learn one of our theorems that's really important for the year, the intermediate value theorem, and that also involves AP writing. So on the free response part of the AP test, they're just picky about how you write things. We have to learn how to do that. First essential question you're trying to look for. Oops, that was a nice typo. Sorry, I don't. This is weird when I'm doing it as a tablet. How do you prove overall continuity for a piecewise function? So we talked yesterday about how to prove it at a point. Today we'll learn if it's continuous everywhere, how would you actually prove it if it is piecewise? How do you find A, B, and C values to make a piecewise function turn out to be continuous? And then how do you apply the IVT? So this is the exact same example from our last packet, but our last packet we talked about how you would answer it if we were doing multiple choice. Well, now we're going to talk about if you have to prove this. If this is a free response question and it says, most likely they would actually just come out and say, prove that this is continuous everywhere for all real numbers. So here is AP writing to prove continuity. Well, since, I put it in tablet mode thinking it would help. It's not helping, so let me take it out. Since this is piecewise, so if it is a piecewise, you need to check the split point, break point, boundary point, whatever you want to call that. That's where the X is. They're giving you the X for the top part and the bottom part. And then you also need to discuss the individual pieces. And what I'm talking about there is, are these pieces on their own okay? So we'll check the split point and then we'll check the pieces on their own. Usually it's kind of a waste of your time if the pieces on their own have a problem. So analyze those real quick and just go, oh yeah, okay, that's all right. But then most of the time where you're going to have a problem is the split point. So I'd start doing my work there and see what I come up with. So if I want to talk about continuity at the split point, let's first discuss, that's a three-step process we learned in the first 1.4 notes, that continuity at x equals 1. Well, so I would first have to check f of 1, and you need to think about, does that involve the top piece or the bottom piece? The bottom piece is where it's equal to. That's where it would be the function value. So that would be 1 squared, which equals 1. Then our second step in the continuity process to just check 1. So in our case, split point is x equals 1. Second point to check then is the limit. Goodness, my hand is just hitting all these different things at the bottom. Okay, the limit as x goes to 1 from the left, is that the top or the bottom piece? Less, oh my gosh, less than 1 would be left. So that's going to limit of f of x, because you got to take the limit of something. That's going to be negative 2 times 1 plus 3. It's going to be 1. Then let's check the limit as x goes to 1 from the right of f of x. Now that was when you were larger than 1, so that's that bottom piece. And so that would be 1 squared, which is 1. Those are equal. So overall, the limit as x goes to 1 of f of x equals 1. That's the second part. So if you want to kind of do bullets as far as the definition of continuity, that's the first bullet. This is the second bullet. And the third bullet for definition of continuity would involve those first two pieces being equal. So then we would say, since f of 1 was equal to the limit as x went to 1 of f of x, and we already showed that up above, so you don't even need to tell them that that's 1, but you could if you wanted to, equals 1. Since all those are equal, f is continuous And how you decide where you're talking about is based on this, at x equals 1. I just wanted to clarify that with some color because when I input the 1, I also got out 1, and that can be kind of confusing. Your continuity is at the value that x was approaching, so as x approaches 1. Okay, so we proved continuity at a split point. That's done. We've done it with AP writing. Okay, now we need to talk about AP writing for the individual pieces. So then we would say, note that negative 2x plus 3 and x squared are continuous for all real x, so for all x and r, if you want to use some abbreviations. Okay, how I've organized mine, I made a numbered list. So if you do that, then you can say by 1 and 2, then f is continuous for all x in R for all real x. So some things we need to talk about. The logic first. The logic is it okay where I split here? Then were they okay on their own? And before I would write it, I usually write it out last, but I would think about it first. Because if you have a problem right here, then you might as well go ahead and add that to your list, and you're not going to prove it's continuous everywhere. But we checked both. If you want to do continuity, show continuous at a point, you have to check all 3 conditions that we talked about yesterday. And then we noted the pieces were okay on their own. Well, then you can join all that together and say, okay, they were okay on their own, and they were okay at that point that they may have a break. Well, they didn't have a break, so I can join all that together and say it's continuous everywhere. Now, you do have some freedom in how you want to organize your argument. Some of you are really good writers, and so instead of labeling step 1 and step 2, you might say by my aforementioned points or whatever. It depends on how logically you're able to construct an argument. I'm showing you an example that's pretty linear, pretty good for how math kids think if they don't want to write a lot. This is a way to organize your thoughts. Do a bulleted list, do a numbered list, but it is by no means the only way to do your writing. You need to write how you feel comfortable, and then you need to go back and address, did I prove that it was continuous at the split point? And that involves a 3-part definition of continuity. Then, did I discuss that the pieces were okay on their own? And then, did I tie it together? So I guess the last step would be a tie together, if they're all coming out okay. Okay? You're going to need to practice this and get some feedback on your writing if you want to do it a way that makes more sense to you. But you will be okay as long as you have proved it's continuous where it splits, you have discussed that the pieces were okay on their own, and then you have tied that all together. Okay, as I go through and do a little bit more. So a different piecewise example. All right, you can either take a look at the graph or you can take a look at limits. It's whatever's easiest for you. We're kind of struggling with graphing, and this one's pretty easy to graph, so I'm going to take a look at showing you how to graph it. This, darn it, I hate when it does that. Okay. This is a parabola as long as x doesn't equal 1. And it's a really easy parabola. It's just been shifted up 2. Well, okay, so at 1, I'm not going to be where this parabola is, but everywhere else I am. So at 0, the parabola is at 2, and then don't draw right now. It curves up like this, but it's not equal at 1, so I'm going to hollow it out. That's the idea of what this function means. It's a parabola as long as x doesn't equal 1. Okay, let's go and do that for real. So shift up 2, put a dot there. Where is it at 1? Well, 1 squared plus 2 is 3. So my dot sorry, my open circle should be at 1, 3 like that. And then by symmetry, it's at negative 1, 3, and it curves like this. Okay, so this is my parabola as long as x is not equal to 1. Then what happens if x is equal to 1? I plug into the other value, so the other formula, negative 2 times 1 plus 3. So negative 2 plus 3, I get 1. It's not writing. So my dot, oh my goodness, my dot should be at 1, 1, like that. This is a graph of f of x. And it's an accurate graph. If you label your units and everything, this would be perfectly acceptable for AP. I'm doing it just to show you guys as a heads up, when I've glanced over your homework, we're not so great at graphing piecewise. So I wanted to just walk through it with you. If you want to approach it with limits from the left and the right and everything, then go ahead and do that. Let me clean up some of this random dots. Okay. All right, so I have a graph to look at. Now from that graph, you need to decide if I have continuity or not. Is this graph continuous everywhere or not? Hopefully you say, hey, heads up, there's a problem because I have this open dot and then this filled in one. That is a discontinuity. We need to decide if it is removable or non-removable. Hopefully you can remember, since it's a whole, F has a removable discontinuity. Discontinuity at x equals 1. And if this is for AP writing, we could clarify that the removable discontinuity is a whole. It's at x equals 1, and if I have to really explain my reasoning, it's because the limit as x approaches 1 of f of x exists. There is a limit. The limit is 3. The limit is up here as I'm coming in and coming in. So that's what makes it removable. This would be acceptable AP writing. You've justified why. It's because that limit exists, and you have shown them a visual for why you answered what you answered. Now, if you choose to approach it with finding limits instead, then you would have to go through and talk about how the top part has a limit, but they don't come together. And we could go through that. We're going to go through several more examples to kind of show you different examples of writing. But you could always ask me to go through one-on-one a different way to do a problem. Okay, now let's consider what they've changed down here. The only change is that it's plus 5 instead of plus 3. So what happened is at x equals 1, then I get negative 2 times 1 plus 5. That's 5 minus 2, that's 3. So it's the same graph as above. But the whole of 1, 1 that we saw up there is replaced with, oops, sorry, the whole wasn't at 1, 1. The dot, let's erase, not the whole, the dot at 1, 1. The dot that was at 1, 1 was replaced with a dot at 1, 3, and that dot filled in our hole. So this F is continuous for all real x's, for all x in R. Because what that actually looks like, if you were going to go graph it, we would have plugged into negative 2x plus 5 instead, and so the negative 2x plus 5 would have switched our height to come out at 3, and it would have filled in this dot. I'm going to undo that. I wouldn't do that on yours. You could redraw it down below if you want to. But it literally just filled in the dot. So there's the dot as is for the example in number 2, and here's the example we just looked at down below, filled in. There's the dot for number 2, here it is filled in. That's what the change is by swapping that 3 out for a 5. So then they're going to ask us, what setting? Then they're going to ask us, hey, what about this f of x? Find an a value that's going to make it work. Well, we could say then from the above 2 examples, if a equals 5, then f is continuous for all real x. Well, we're going to start to see questions like that. So now if you turn the page, they're going to say, okay, here's one. I'm going to leave an a value and you need to find it. Tell me what a value is going to make it continuous everywhere. Okay. Well, the a value that's going to make it continuous everywhere is that I want my pieces to match. Now, if they don't make me prove it with AP writing, if they just say find the constant that will work, I want my pieces to match. So I'm concerned with x equals 4 because that is my split point. And that's where they may not come together. Because if I look at it on their own, the top part is a line because it has degree 1, just plain x, and the bottom part is a parabola because it's squared. So I really can just hone in on this split point and see if they match up or if they don't. I don't have any continuity problems with the pieces on their own. So if this is, I don't want the eraser. If this is for multiple choice work, we would be fine to only include making the pieces match and how that works. So for multiple choice work, we would be fine to talk about, I want the pieces to match at x equals 4. So plug in 4 to both pieces. So if x equals 4, then ax minus 2 would equal a times 4 minus 2, so 4a minus 2. And then x squared would equal 4 squared, which would equal 16. I want to see if the pieces match. So I want these to equal because that would mean that my line and my parabola would come together. Sorry. So I'm trying to find the a to make that happen. So I want to know when 4a minus 2 equals 16, I can solve that equation. Add, goodness sakes, add the 2 over. 4a equals 18. Divide by 4. A would be 18 over 4, which is the same as 9 over 2. Okay, they said find the a value. Here's the a value. What this means as a side note, I don't want it over there because you should leave that white for your questions. What this means as a side note is that f of x written as 9 halves x minus 2 and then x squared. That function is continuous everywhere with x greater than 4 on top and x less than or equal to 4 on the bottom is continuous for all x in R, for all real x. That's what that means. Okay. They didn't ask us to write that out, but that is what that has told us. Okay. So we've seen some examples of what it means to be continuous everywhere if I have a piecewise function, and then we saw an example of AP writing to actually prove continuity everywhere. It just depends on how the question's phrased. If they aren't going to ask you to prove it, then sometimes you can get away with just what you would do for, for multiple choice work. Okay. Now we need to take a look at what's called the intermediate value theorem, and that's the second part of this lesson. And it's a theorem. You are going to have to quote this theorem. You need to memorize the IVT. You need to know how to write it out, because for AP, if you want to use a theorem and you don't write out all the initial steps that you're supposed to, you don't get any credit. So we're going to do this with the picture down below. If, this is an if then. So if, then here's what's guaranteed. Do everything about the if in blue. What it's really asking us before we get that far is visually, if you have a continuous function, is it possible for you to connect these dots without crossing the dashed line? And you can pause it right now and try on your own. Is it possible to draw me some weird function, but that's continuous? So you can't pick up your pencil, but you got to get from one dot to the next and not cross that line. Try it out. See if you can get anything. You should be coming up with, it's not. You can have, I don't want Outlook. You can have like all kinds of weird ways to connect the dots, but somewhere you've got to cross the line because you've got to get down low enough to get there, to get from one dot to the next. Okay, so we're going to illustrate this with a picture. If f is continuous on AB, on the interval AB, if f is continuous on the interval AB. Okay, and that's what I'm looking at here. Here's the interval starting at A and going to B. Yes, it's continuous. Then we have another piece. If f is continuous here and, so second piece, k is any number between f of A and f of B, I'm going to call this value k. So if f is continuous and k is between f of A and f of B, so you would write that out. Then by IVT, that's our abbreviation for intermediate value theorem. Then what IVT tells us is there's a C in, and it's also in the closed interval A to B. So there's a C that lives here with f of C equaling k. I didn't mean to do that. With f of C equaling k. That means that there is some C. I'm going to go ahead and just connect these dots. So maybe something that looks like that. This tells me that I have to have some C value in here where the height, when I trace it up, gets me over to K. Well, I can find that because I can trace K over and come down here. This is the C value that IVT guarantees me has to happen. So if I meet the first two examples that we've talked, or first two conditions that we've talked about that are in blue, the if part of the theorem, if f is continuous on A to B and k is between f of A and f of B, then I'm guaranteed the part in red. I'm guaranteed that there's an x value in here, a c, that tells me f of c has a height of that k. It's not going to make a whole lot of sense right now. If you can at least, hold on. Okay, sorry about that. That was an announcement that came on. Okay, I don't expect that you right off the bat know, okay, I know every way to apply IVT in real life and whatever. But if you can follow this picture to break down the theorem, if you want to use IVT for AP, you must mention that you've met all the conditions in blue. And then you can say, hey, I'm guaranteed this part in red. The real life part, let's get to that in a minute. Let's try to just apply this theorem. So verify that the IVT applies. That's like actually going through and checking all the steps. So let's do that. So if I want to verify that it applies, I need to know what f of 0 and f of 3 are. So here's my function. Here's my interval. Let's check f of 0. This would be without a calculator, but if you zero out all the x's, you're going to get 12. And then f of 3, you can pause it and do the mental math if you want to. F of 3 is equal to 3. I need to know, the reason it's called an intermediate value, that's an in-the-middle value. I want to know if this value, this is my k, that the theorem would guarantee, I want to know that 4 is in between those. It's an intermediate value. So then I'm okay to try to apply the intermediate value theorem, but the intermediate value theorem makes me check continuity of f. So for AP writing, here's how you can write out the theorem. We're not going to say if anymore. We're going to say since f is continuous on the interval we're talking about, 0 to 3. Well, I just kind of wrote that down, but are we sure f is continuous? What does f look like? F is an x squared graph. An x squared graph is a parabola. Is that continuous? Yeah. So I'm okay to just go ahead and say it. I don't have to prove it. Since f is continuous on the interval 0 to 3. And then I had to talk about this k value. So this 4. And you can say this in several different ways. You could say 4 is between, like literally in words. F of 3, oops, sorry, f of 0 is probably what most people would start with. F of 0 and f of 3. That's one way to say it. Another way is to say it with symbols, to literally put 4 in the middle. And then if you want to always do like the smaller x first, f of 0 and then f of 3, then you have to decide what makes that true. F of 3 was the was the smaller one. So f of 3 is smaller than 4. So you would need it pointing to f of 3 and eating or opening towards the 4. And then 4 is smaller than f of 0. So f of 0 is greater than 4, which is greater than f of 3. Or you could put 4 in the middle and put it in order of what was smallest to largest. F of 3 was smallest. You could say less than 4, less than f of 0 was then biggest. You only need to pick one way of writing this. Not all of them. But if you go back to our theorem, we had to talk about continuity, which we did, and then we had to talk about this k value, which we now did. Okay, then going back to the theorem, since that's all true, then I can say, then by IVT, there's a C in the closed interval still 0 to 3 with f of c equal to that intermediate value. Well, what is the in-between value? The in-between value is 4. Intermediate for in-between. I need to be talking about an in-between function value. Well, all of that just verified that the IVT works and went through the proof of how you would write up IVT for AP writing. Then they ask us another question. Then they come back and say, find the value of C. Well, that's an algebra question. That's just find when f of x equals 4. You don't need to know anything about IVT to do that. But they're saying, okay, we've proven that f is going to be equal to 4 somewhere. We used IVT to prove that. Now tell me where. Well, okay, so, goodness. So f of x, oh my gosh, I don't want Outlook. So f of x is x squared minus 6x plus 12, and that's equal to 4. Then I can set that equal to 0, so subtract the 4. X squared minus 6x plus 8 is equal to 0. I can factor because it's a quadratic. X minus 4 x minus 2 equal to 0. I can set each factor equal to 0 and get x equals 4 or x equals 2. But they say find the values of c that are guaranteed by the theorem. The theorem talks about c being in 0 to 3, the closed interval 0 to 3. That means this is my only c. C equals 2. Because it has to be in the interval 0 to 3, and 4 is too big. A lot of times for AP, you're not asked to do both of those things. A lot of times for AP, you're just asked to prove that it applies. So although the part we did first was long, that's the part you need the most for AP. Some other examples that you need for AP, for intermediate value theorem. You can prove that a 0 exists. If you say maybe f of A is positive and f of B happens to be negative, and we also know that f is continuous on A to B, then that means, so if you draw that out, if this is A and f of A is something positive, and then mark off B and f of B is something negative, and you know it was continuous, so you know you connect the dots between them, then to prove a 0 exists, that means that it has an x-intercept, sorry, not an x-axis, an x-intercept. This is where you're trying to show the in-between or intermediate value is k equaling 0. Yes, I can prove that it crosses the axis if I know it started above and ended below and it was continuous everywhere. Or vice versa, if I know it started below and ended above, started negative, ended positive. You'd have to do the AP writing for it, but that's an example of how it works. Okay, last thing we're going to finish up and go through before you try some is a calculator question from AP. And it's a calculator question because you can draw a graph of this function on a graphing calculator. Okay, I'm not even going to bring mine up necessarily. Maybe I need to. I'll bring the calculator up later. First, I'm just going to give you the values, but we will talk about the calculator if you need help. Okay? So if it is a calculator, something to know, AP grades 3 decimal places. You have to be accurate to 3 decimal places. Okay, we have a table of values, and if you remember, a fancy term for that is between numerical, graphical, and analytical. This is a numerical approach when they give you a table. Then we're going to take a look at a formula that they also give us, and that's going to be a graphical approach because we're going to use our calculator. So water is pumped into a tank modeled by this formula for W. So my rate in is W. And then water is removed from the tank, so the rate out is modeled by R. So pumped in and then removed. Some other things that are interesting to know, I might need units. I for sure need some kind of interval, and they're telling me that interval. So they tell me the rate in is for 0 to 8. They also tell me when it's leaving that that's also 0 to 8. They tell me that R is differentiable and decreasing. This differentiable piece I need to update you on because it's a vocab term you're not going to learn until next chapter. But we need it right now to know that this means R is continuous. We'll talk about why in chapter 2. Okay, at time t equals 0, there are 50,000 liters of water in the tank. Now let's actually get to their question. Is there a time t when the rate that it's pumped in is the same as the rate that it's removed? Explain why or why not. Okay. Well, we can do graphing calculator and check out graphing calculator to graph W. And I'll pull up mine as a separate kind of tutorial video if you need help for that. Okay, but then I need to prove that they are the same, but I can't graph R because just because I know these values, I don't know how to connect the dots. We need to decide if I even can connect the dots if we think R is continuous, but it is. We knew that R is continuous, but even still, knowing a bunch of dots doesn't mean that they connect all nice. What if they do like all kinds of weird stuff in between and you don't know that? So I can't graph R. I can use my calculator to graph W, but I can't graph R. So a graph alone isn't going to help me. I'm just going to come out and tell you this is for us, we're supposed to be using IVT. So if we're going to use IVT to do this, I need to figure out where these functions are at the beginning and at the end. So let's figure out W of 0, and that would be from the graphing calculator, or just if you zero out, 0 over 20 is 0. E to the 0, anything to the 0 power is 1, and so that ends up being 2,000. So you can do that without a calculator. But W of 8, that is with the graphing calculator, and it's 81.524. Go ahead and just write it down now. And if you struggle with your graphing calculator, then let's check. And we're going to talk about on your graphing calculator, you should see that it's continuous. Okay. All right, then let's find our information for R. Well, that's just from the table. Read the table. R at 0 is 1340. Look up at the table. And R of 8 is 700. Okay. We know that they are both continuous. Okay. We knew that W was continuous, and we knew by them telling us differentiable that R was continuous. So both continuous functions. Okay, so I don't know how to connect the dots, but this is just a sample. What's happening? Okay, I need to know what happens at 0, and I need to know what happens at 8. If I just make a mark up here and call this 2,000, then here would be 1,000. W at 0 starts at 2,000. W at 8 is way down in comparison. If this whole mark is 1,000, 81 point something is pretty low. Okay. Then, and I connect the dots. I don't know how. Actually, I do because I know what the graph of an E function looks like. It curves down like this, something like this. Okay. But if you don't and you haven't pulled up your graphing calculator yet, this is just a sample. R of 0 was 1340, so that might be like here-ish. And then R of 8 was 700, so like maybe here-ish. And you connect the dots. We have no idea what happens. Like, we really don't, unless we want to plot all the values in between, and still, like we talked about, in between, we don't know. Okay? I know at the very least that to get from one to the next, they had to cross once. But this is an example as a sample one where they crossed several times. So yes, there's at least one time, I think, because even if I undo my drawing of R and I draw just a real simple connect the dots for R, maybe it just goes like that. At the very least, they have to cross one time. They have to. Okay? So they must intersect at least once. Okay, well, if they must intersect at least once, and that's all it's telling me, is there a time? There might be several, great, but there has to be one time. Okay, let's go ahead and prove that. And a way to prove that, so far, I'm telling you, we want to use IVT. So for IVT, I need a function equal to a number, because that's what IVT proves. Well, if you remember, if we talk about intersection points, that also means if we were to subtract them, they would have to equal 0. Because I basically want to know that sometime W of t, my rate in, and R of t, my rate out, are equal. Well, that means that W minus R has to equal 0, right? And then, aha, you have what you need for IVT. This is going to be your K value that you're trying to show. And this is going to be your function. Let's do our writing. So for our proof, this would be like AP Central, you're good to go for your score for AP. So for proof. All right, we need to talk about, since we begin with R, let's do the 0. We begin where the W, the rate in, was taller. The red part was taller. So we begin with W of 0 greater than R of 0. At first, my rate in is higher than my rate out. And then we end with R of 8 now greater than W of 8. It flip-flopped. By that flip-flop, that's how we know they had to cross. Because they can't cross each other. If one starts higher but then ends lower, then they can't cross each other. If one starts higher and doesn't end lower, starts higher, stays higher, then they might not cross each other. But if one starts higher and then ends up being on the low end, then they're going to have to cross. Okay, so since that is true, since we begin with that, we know that W of 0 minus R of 0, because I'm going back to this whole function idea, we know if W is greater, and then I would subtract, that would be greater than 0. And then if I were going to subtract again this way, let me pull this off to the side. If you do the subtraction here, you get that R of 8 minus W of 8 is greater than 0, but if I want to put that in the other order, do 0 greater than W of 8 minus R of 8, then that really means that this is smaller than 0. So I could say, and W of 8 minus R of 8 is less than 0. Okay, so I've shown on one side that I was greater, and I've shown on another that I was less. This is like the whole positive negative thing. All right, since we begin with that, we know that this is true. Okay. Also, W and R are both continuous functions. And if you don't specify where, that means they're continuous everywhere. Okay, but we could say we know they're continuous for the W everywhere, but we know only about R from 0 to 8, so we're going to say continuous on 0 to 8. Okay, so by IVT, these top two pieces have been meeting the if part of IVT. This is now so by IVT, there's a T in 0 to 8 with my function. If I've shown somewhere that it's greater than 0 and I've shown somewhere that it's less than 0, then IVT is going to show me that it equals 0 somewhere, because 0 is my in-between value. Just like on the last page, if you go back, I showed something greater, something less. 0 was my in-between. Same idea. I showed something greater than 0, something less than 0. 0 is my in-between. So there's a T in 0 to 8 with W of T minus R of T equaling 0. That means, meaning W of T equals R of T. And that's what we wanted. Is there a time T where that happens? Yes. By IVT, I've guaranteed it. Again, these top two pieces are like the if part, and this bottom piece is like the then. But I'm not saying if, because if leaves it up in the air. Like if this happens, then this happens. Well, I'm going to confirm that yes, the first part happened. So then I can guarantee by IVT that the second part has happened. Okay, real life examples. I would really encourage you to click on the link that was a couple pages back and watch it. It gives you a real life example of something called the FAT project. They did an experiment, they ate fast food every day, and then they charted their weight. And it explains to you the IVT in that context, which is really nice. Then also just some other real life examples are age, height, weight, and we can talk about those in class a little bit more. But you know the IVT, and you've now seen several ways to apply it. Your job is going to be to work on your writing and make sure it's AP quality. Okay. I will do a separate video if you want help on the graphing calculator, last page, where we had to graph this W of T. If you want help on the graphing calculator with how to graph it and how to find the value for W of 8, I'm happy to show you that. So I'll do a separate video on that. And it may take me late tonight or tomorrow to get that up.